So now we're going to look at putting this all together. We're going to look at how the different things we've talked about use different parts of the processor and how they share different parts. So we talked about ALU operations, these are add and OR instructions. Talked about memory access, load and store. And we talked about instruction fetch, and those are in particular branch instructions, which control what sort of instruction fetch we do. Now let's walk through these and see which parts of the processors they use. So all of these instructions start out by loading the instruction. You're doing a branch, a load, store, and an add, you always have to load the instruction first, and then you calculate the next PC. So all of these are going to use the program counter, the instruction memory, and the adder for that part of the instruction fetch. After this, they're going to go and read the register file. So ALU operations read the register file to get their data. Memory access instructions read the register file to get addresses and data if they're stores. And branch instructions read the register file to see whether or not they should branch. Remember, they're doing an equality comparison. So we're going to read the register file. Then the ALU operation is going to use the ALU to actually do the operation, the add or OR. Memory access is going to use the ALU to calculate the address. And instruction fetch is going to use the ALU to do a branch comparison. So it's going to do a subtraction to see if the two register files are the same. So all of these are going to use the ALU. After that, the ALU operation is going to write back the data to the register file, and memory access is going to write the data back to the register file, at least if it's a load. So we're going to write to the register file. Now before it can write back to the register file, the memory access needs to read or write the data memory. It needs to go get the data from the actual memory. So it's going to use the data memory. The instruction fetch doesn't write back to the register file. If we have a branch instruction, what we're going to do is we're actually going to update the PC. So branch instructions are going to write back to the program counter with the address of the new branch. But before they do that, they need to go in and calculate the branch address. So you can see for instruction fetch, we have two things we need to calculate, the branch address and we need to do the branch comparison. So looking at these different parts of the processor, we can see that most instructions are going to use most parts of the processor. This means we can share the same hardware across all of these instructions. You'll also notice here that the instruction fetch needs to do two calculations. It needs to both calculate the branch address and do a branch comparison. So we only have one ALU right now, so we're going to have a hard time because we can't use it for two things at the same time. So now let's go on and talk about how we connect up the register file and the ALU. So we already covered the basics of this. We're going to take the first output from the register file and run it into the ALU, and take the second output, put it to the ALU. This is what an R-type instruction will do, two inputs from the register file. And then we'll take the results and we'll write it back into the register file. So that makes sense. Now how do we add in the memory? Well, here's our data memory, and we need to hook it up. So the first part we're going to hook up is the data that goes into it. So this right here is the data from the register file that gets written into the memory. Second part we need to hook up is the address. So remember, the address gets calculated by the ALU. So we need to take the address from the ALU and send it into the memory. And then finally, we need to take the data we read from the ALU and figure out a way to get it back to the register file. So this connection takes the memory data from the data memory and writes it into the register file. So now we've got the data set up. But we need to figure out how to calculate addresses. And remember, addresses use immediate values, so we need to figure out how to get immediate values into this. So for immediate values, we need to sign extend them, because we know we only have 16 bits of immediate value in our instructions, and those 16 bits come from the instruction. So we're going to take the data from the instruction, put it into the sign extension, and then put it into the ALU. And this will allow us to use that sign extended immediate value in our calculations. So here's that immediate value coming from the instruction. So here's a question. What is the 0 output from the ALU used for? So this output is used to decide if we take a jump. So if we have a branch equal instruction, the ALU is going to do a subtraction, and we're going to use that subtraction to decide if we do a jump. So adding MUXes. If you look at what we have in this graph here, we can't just go in and merge wires together in these places. So we've got two places in our picture here where we have wires that just come together. And we can't just merge them like this because we get garbage signals. So we need to put in MUXes instead. So let's take a look at those MUXes. Here's the first MUX, and it's the input to the ALU. This MUX chooses the ALU input. It selects either the register file, or the sign extended immediate value. The second MUX over here is selecting the data that goes to be written into the register file. So this selects either the ALU result or the data from memory to be written into the register file. So here's a question. For this MUX here, what should the value be for an addi instruction? That is an add immediate instruction. Should it be 1 or 0? Well, the value here should be 1, and that's because addi takes one operand from the sign extended value and one from the register file. So one operand from the register file, one from the sign extended, and so that means we have to select input 1 on the MUX. So what should ALU source be for the add instruction? This is not add immediate, this is a regular R format add instruction. So should it be 1 or 0? Well, here it should be 0, and that's because add is an R format instruction and takes two operands, both of which come from the register file. So we need both of our operands from the register file, so we need to select the 0 input to the MUX. Now, let's talk about building the branch unit. So what is the branch unit going to do? Most of the time, it's going to do what we saw before, PC equals PC plus 4. So we take our program counter, take the output, put it into our adder, add 4, and then we put it back into the program counter. However, when we have a conditional branch instruction and we take the branch, we do something different. Here we're going to do PC equals PC plus 4 plus the sign extended immediate value from the instruction, left shifted by 2, but we only do that if we're supposed to take the branch. So let's take a look at how we build that logic. So the first part we need is the sign extended value from the instruction. So we put it through the sign extension, and now we've got that value out. Now we need to shift it left by 2, so we're going to put in a left shifter, and then we need to add it. So we're going to need another adder so that we can add it in. And what do we add here? Well, we add that sign extended shifted value, plus we add PC plus 4 from our previous adder. Now the result of this is going to go into a MUX, as we need to choose which branch jump we're going to take, and then this is going to go all the way back into the PC. So this is the path for when we take a conditional branch. So here's a question. Why do we have a second adder for branches? Is this because we need fewer bits for this adder? Because the ALU adder is needed for testing equality? Or because we need a special adder for the intermediates, for the immediates? Well, the answer here is the ALU adder is needed for testing equality. When we have this branch instruction, we're already using the ALU for something else. Remember, we're taking two register values, we're doing a subtraction, and then we're generating this 0 output. And that 0 output is used to decide if we do a branch. So we're already using the ALU for that comparison, so we need another ALU, another adder, in order to calculate the address for the branch. So let's take a look at some of these signals. When do we select the output from this adder instead of the regular PC plus 4? Well, the trick to this is to look at this 0. So we decide to take the branch when we have a branch instruction, and the 0 out from the ALU tells us to do that. So the answer is when we have a branch and ALU 0 out tells us to branch. So if we have a branch equal, then ALU 0 means the two values are equal and we should branch. If we have a branch not equal, then ALU 0 being 0 says they are equal and we shouldn't branch. So we branch depending on whether it's branch equal or branch not equal and the results of ALU 0. So here's a question about branches. What operation does the ALU do on a branch? Does it do no operation? Does it add to compute the address of the branch? Or does it subtract to compute equality? Well, in this case, we want to generate that 0 out. So in order to generate the 0 out to see if two registers are the same, we need to subtract to compute equality. So the answer here is the ALU subtracts the two registers to see if they're equal on a branch. So a question about loads. What does the mem2reg MUX select for a load word instruction? This is the MUX coming out of the memory. What does it select? Well, in this case, it's going to select the read data from the memory. Because we're doing a load word, we want the data to come from the memory and get written back into the register file. So we're going to select the data memory.